what we give, step input, ramp input, and then we have the sinusoidal or harmonics, whatever we call it. A harmonic function we can give, which generally consists of sine and cosine waves. And then when we have a unit step function, which is defined as time increases, the value suddenly increases and then it remains constant. For a given unit step function, how a zeroth order system will behave, okay? And for zeroth order system, we have from the definitions of zeroth first and second order system. How do we got those zeroth first and second order systems? The output and input is related by a differential equation, okay? And depending on the power, we have classified them as zero order. Based on the order, we have defined as, if the order is zero, then we call it as a zero order system. If the order is considered to be one, then we call it as first order system. And if we consider the order to be two, then we call it a second order system. For the time being, we have considered these three kinds of systems, and accordingly, we have introduced some terms like static sensitivity for zeroth order system, time constant for first order system, damping coefficient for second order system. So those are the important things that we have looked at in the previous class. Right. So in today's class, in the previous class itself, one second, just in the previous class itself, we also have looked at how a given input, such as for a given zeroth order system, if we give a unit step function, what happens? So that we have looked upon, and based on the static sensitivity, the output will come. There will not be any time lag. It immediately gives the output. There will not be any time lag, but only thing is it produces the input signal in such a way that either it may be higher or lower depending on its static sensitivity. Okay, so and then we have moved on to the unit step function when given as an input for a first order system, and we have taken the same differential equation, and we have formed the output in the form of y equal to Ka plus y naught minus Ka into e power minus t by tau. So here we have got a new term called tau, which is nothing but the time constant. And what it does, when we give a unit step function, because of the
Sir, screen is totally white. We can't see anything.
Just a minute. One second. Sorry. Is it visible now?
Yes, sir.
Unless I don't know what was the problem in my system. Somehow, unless I give the complete screen, it's not. I'm not able to use the cursor pointer, and if I take it as a window, it is not working. That is the issue. So let's move on. So what we have understood in this in a nutshell is, even if we give a step input function for a first order system, they generally have some time lag to reproduce the input as output. Okay, it takes some time to actually reproduce the actual input, and on what factors it depends. It depends on the time constant tau. So we have come across some new terms from the solution. We understood that there is a steady state term and there is an unsteady state term. This is the unsteady state term, what we are seeing over here. This is the unsteady state term. Sorry, y naught minus k into e power minus t by tau is an unsteady state term that is seen over here. And as your time increases, this value becomes negligible, and finally we eventually get the steady state value, which is close to Ka. So depending on the time constant, how quickly we get, if it is small, if it is smaller, what happens? If the time constant is smaller, what happens? Yeah, please answer. What happens if the time constant is higher and time constant is smaller? The response at which it happens will be dependent on this time constant. Okay, so second term, it is an exponential decay term, and the first term is the steady state response of the system. And we have looked at these terms, and then we have defined how it works and all in the previous class. And we have defined some important terms over here. Suppose if the time constant tau is basically is the time taken by the system to reproduce 63.2% of the. That is what we have defined. Okay, so how much time, lesser time it takes to reproduce it, then faster you will be able to reproduce the input. Similarly, we have also defined the rise time, which is nothing but 90% of the input if we can produce. What is the time for that? What is the time taken by the instrument to reproduce 90%? That we call it as the rise time. And finally, for producing the complete input, almost 99.3 or thing, we have to have the time, we have to wait for a time of 5 times. So that is basically your time. Okay. So this is same first order system. We can give an example, like we have a capacitor and resistor connection where we have a voltage difference between them and current is passing through that. So the first order system can be having two types of like this. One is the diffusion or dissipation thing, and the other one is capacitance term. So there are two things over here. Okay, so these first order systems generally have this capacitance and resistance, what we call it as. So either it may be, if it comes to thermal systems, we can call it as thermal capacity. Okay, or if it is electrical systems, measuring systems, we call it as electrical capacitance. Similarly, the resistance may be either electrical resistance or thermal resistance, which is nothing but this is what factor which actually helps in dissipation of the energy. Okay, dissipation of the signal, whatever. So here I have given a very small electrical system where we have a capacitor and resistor and current flows through it because of the voltage difference, and the voltage varies with respect to time, and that voltage response is given by the voltage response is given by e power minus t by tau, e of t by e naught. So that means the initial voltage is in the denominator, and the voltage with respect to time will be in the numerator. Whatever is varying is nothing but e minus e power minus t by tau. I think I forgot the equation here. I will put that equation. Okay, so let me write that expression if it's possible. So it is nothing but capital E of t, that is nothing but voltage at any time t is equivalent to E naught is equivalent to e power minus t by RC. So what is RC here? The product of R and C, the capacitance and the resistance constant is nothing but the time constant. Okay, so that is what we are showing over here. Okay, similarly for thermal systems also we can write it, but it will be in the thermal values. Thermal becomes thermal resistance, and the next term becomes thermal capacitance, not the electrical, and instead of electrical and electrical capacitance and electrical resistance. Okay, so I have given a very small problem over here. Have you looked at these problems? So can you check out these two problems quickly? Somebody? Would be good if you could solve this problem, somebody. So we have given you a very small thing. A certain thermometer has a time constant. He has given the time constant. That means tau is given, which is nothing but 15 seconds, and the initial temperature of 20 degrees centigrade. So initially at a temperature of 20 degrees centigrade, and it is suddenly exposed to a temperature of 100 degrees centigrade. Okay. So now what is changed? Initial temperature T infinity is your is 20 degrees centigrade, whatever the initial thing, and suddenly at time t is greater than 0, it is exposed to a temperature of 100 degrees centigrade. Okay, it is exposed to a temperature of 100 degrees. So what he is asking is determine the rise time and temperature at this time. So there are two things that is asking. One is the rise time they're asking, okay, and the second one is the temperature at this time, and at what will be the temperature at that particular time is what they're asking. Can you solve it? So now tau is given, okay, and what is rise time? Rise time is 90% of what the time taken for reproducing the time for 90% of the input, correct? So therefore what happens is your e power minus t by tau is equivalent to what? 0.1. From this find out what is t. Your tau is given already. What is tau? Tau is given as 15 seconds, right? This one. So you need to find out what is t. Somebody please quickly answer.
Yes, sir. 34.538.
You are getting 34.5. Now, what is the other thing is asking? What is the temperature at this time? So at this particular time, what is the temperature? That is what is being asked. So we know that this value is 0.1. So therefore, T of T, that means at whatever time that we have got, what is the time? 34.54 seconds, whatever we got, minus T infinity is what? 20 degrees centigrade by, what is the sudden change? 100 minus 20 is equivalent to, at this rise time, what is the temperature? That is almost equivalent to 90%, right? So 0.1. Can you find out what is temperature at a time of what? 34.54 seconds.
Sir, in the numerator it should be t minus 100, no, sir?
Why?
Why?
It is initial temperature. Whatever the initial temperature you have taken, the expression that you are seeing. What is the expression? See, y minus y infinity by y naught minus y infinity. Yeah, correct. Y naught is your is taken to be the initial temperature. Correct. Therefore, the expression becomes correct. The other way I have to do it. The equation becomes T of T minus 100 by 20 minus 100 equal to 0. Are you getting the same answer? Yes?
Yes, sir.
You are getting the same answer, right?
Yeah, yes.
So that's how you are finding out. Similarly, if they are asking you anything in these parameters, you should be able to answer. I hope you understood that. T minus T infinity, it's not 20. Let me change that. It's 100. T of T minus 100. Okay. Later you may be by 20 minus. It's a simple thing on the simple equation. This equation is nothing but e power minus t by tau. This whole value is nothing but e power minus t by tau. Okay. So that is one. So second problem, can you check it out? There is a 10 microfarad capacitor is charged to a potential of 100 volts. They have given the voltage. At time t0, it is discharged through a 1 mega ohm resistor. Okay. So what he is saying is the resistance also is given. It is 1 mega ohms. It's just asking what is the time constant for this system. So for a capacitor and resistor system, what is the formula for time constant? Time constant formula is tau is equivalent to resistance into capacity. Electrical resistance into electrical capacity. Take the this thing, and then you should get in terms of tau in terms of seconds. So based on that, you try to find out what are the units. Okay. So now the third one, you can take an ordinary mercury in-glass thermometer and indicate which parts corresponds to which stage of measurement system. So this is already we have seen in the with the Bellows type of pressure gauge. So similar kind of thing. So this kind of things you can expect in the mid exam, minor examination. Okay, so let us move for today's class. Okay, so now we will continue with the response to the changes of input for a unit step function. So let us continue with the second order system. For example, if we are giving a step input, okay, if we are giving a step input for a second order system, how it will behave? We have seen in the earlier case, there will be some kind of delay in producing the output if it is a first order system for a given sinusoidal input or harmonic input. Similarly, if we have a second order system, we have already defined the second order system like this. So x of t, y of t equivalent to this whole thing, right? We have written it. So depending on the power, the other terms we are neglecting, a3d d power 3x by dt cube, a power 4, those terms are neglected because we are only considering up to second order. So this is the expression that we get, right? So this kind of a system we are generally calling it as a second order system, second order instrument. And now when you give this for this second order system, when you give the time t is greater than 0, if it is constant f1, at time t equal to 0, the function is 0. So with this initial conditions, y equal to y naught at t equal to 0, so the above equation can be considered. So this expressions you have already seen, we have converted that in this particular form where omega and zeta we have defined in the previous class. So if you remember, zeta is the damping coefficient, omega is n is the frequency, natural frequency, and k is the static sensitivity. So the same term, if you rejiggle the mathematical equations, we will end up with this kind of an equation. So for these conditions, like when the input is given for this boundary for these conditions, and what is the initial condition, y is equal to y naught at t equal to 0, and y equal to f1 when t is greater than 1. So for these conditions, you can see that we are not only getting different solutions depending on this expression. So this is the general equation, general solution for this differential equation. This is the general form of the differential equation where you are getting the zeta value over here. So zeta value, if it is varying, automatically when this value is changing, automatically the solution is also getting changed. For example, if zeta is equivalent to 0, that means the damping coefficient C by Cc is equivalent to 0. So that means what? There is no damping system at all in the particular measurement system. You are not providing any spring or anything in the particular viscous liquid or anything into the system. Okay, so in the first case, why it is required a damping system? Just think you have a needle and a pointer, and there is an input facility. Why do you need a damping system? So when there is a vibration, you require to have a damping system, right? Why you are using that damping system? The damping system actually tends to oppose the motion, right? So in order to bring it to an equilibrium position from the oscillation at any particular equilibrium, if you want to bring it to, then we generally use a damping system, isn't it? So if the damping coefficient is not at all, the damping coefficient, critical damping coefficient is equal to 0, that means it is basically an undamped system. Okay, it is basically an undamped system. Okay, so that means there is no damping system. So for this, we have one solution. And suppose there is dampener and the damping system is there, but its value is less than 1. So the damping that we have provided is less than the critical damping coefficient. Then zeta is less than 1. Okay, so in that case, you will call it as underdamped system. Okay, we are not potentially dampening it completely. So the third one is critically damped system, where your C is nothing but Cc. The critically value, whatever is there, we have provided the damping system of that value. So that one, it reaches the dampening, reaches to that value. So that one we call it as a critical damped system. And suppose if the dampening system is having over damping, that means zeta value is 1. That means your C is greater than Cc, then we call it as a over damping system. So for each value of these systems, we will get a different solution for this. Okay, so how it behaves when it is an undampered system, when it is underdamped system, when it is critically damped and over damped, they have plotted, and then from the plotting system we can understand how it will behave. Okay, with the different inputs, with the different static or unit step functions. Okay, so now you can see over here, when zeta is equivalent to 0, your solution is nothing but yt by ys into 1 minus cos omega n of t. So what it does, so when you are giving a static input, suddenly the input is raising over here, but however the output is taking certain time to reach to the to produce the same input. So this time we are calling it as the rise time. Okay, now this is what we are creating, the rise time, but you can see some oscillations over here, right? It's not it's not an increasing kind of a thing and then settling down, but it is kind of some oscillations you could see here. After that, it's getting settled. Okay, so similarly, if it is zeta value is 0, then the solution we are getting in the form of natural frequency into 1 minus cos of omega n into t. So if it is an underdamped system, we are getting a solution like this, where you can see that you have sine and cosine waves over here. So what it does, what is the sine and omega cosine values will say that is the output will oscillate after the step input is applied. Once you apply this, there will be oscillation, and what is the frequency of this oscillation is given by omega d is omega n into 1 minus zeta square. So here omega is basically a frequency. Okay, so the third one is your critically damped case. When the third case is when zeta becomes equivalent to 1, we requires the solution to be, we will get the solution to be like this. Okay, so we are seeing an exponential value over here, exponential decaying value over here. So all of these values we have plotted, just mathematical solutions I'm showing. It's not of any importance. Only thing is you just need to understand how they behave. So no need to mug up or solve these equations anymore. The fourth one is the overdamped case, where your zeta is greater than 1. So in that case, the solution we are getting is this. So we have hyperbolic sine and cos, hyperbolic cos values also getting into the particular equation apart from its amplitude sensitivity. So when we plot all those values, okay, with respect to its natural frequency and its ratio of its input and output, you could see over here when zeta values are like this. You can see when zeta value is 0, that means what? Undamped system. For example, if it is an undamped system, what happens? We have given an input and the output starts like this, and then it goes, and then it again oscillates. It keeps on oscillating. You can see over here, it keeps on oscillating, but never comes to a steady state. It keeps on oscillating. If you are not providing any damping to that, so the first order system for a given step input will never reach an equilibrium state. It keeps on oscillating like this. For example, torsion, if you see the dynamometers, so you can see the needle will keep on fluctuating. It will not come to a constant position. Even though we are there, the load is dynamic, but still, example for your viewing, whenever we get a chance in the thermal engineering lab, I can show you that it keeps on, initially there will be huge vibrations, and then slowly it will not come, after its vibrations, it will not come to a particular position. It keeps on moving. So that is the nature or the behavior that the first order system will execute when you give a step input for zeta equal to 0, C by 0. For underdamped systems, right? Underdamped system means what? When the damping is less than, when your zeta value is less than 1 but greater than 0. So those kind of things will behave. You can see over here in this figure, you can clearly see this 0.2, 0.4, 0.6, and 0.8, and 1 is basically your critical damper system, right? So less than that, that means up to 0.8, look at the curve, how it will behave. The value will start, you have given a step input, the value will start of 1 unit step function, so that means after t is greater than 1, the value has to be shown like this. In general, it takes, if it is a first order system, it will take a rise time and then suddenly it becomes, but here, in the second order system, due to dampening, if it is undampened, this keeps on oscillating like this. Okay. Whereas if it is 0.2, the blue color, you can see over here, it oscillates and slightly it becoming steady state. It comes towards steady state. 0.4, you can see there is a slight green color. You can see this, and then it becomes steady. And 0.6, you can see the red one, immediately it's getting. And 0.8 is almost behaving like a first order system. But when you look at the 1, that means it's critically damped. For that, you can see that there is a rise time and then it will be coming to a steady state. There will not be too many oscillations. Okay, now there is an interesting thing is you have over damper system. That means you have 1.2. Okay, so it also reaches the steady state, but you can clearly see that it takes more time, right? The time delay is more over here. Okay, it takes more time to come to the steady state compared to the critically dampened system. So over dampened system is taking more time but less oscillations. Okay, it slowly shows, there is not oscillations, it slowly comes and shows. You can imagine a pointer and a scale kind of a thing, just for your understanding. I'm just saying for your understanding. But imagine that it to be a scale, sorry, a scale kind of a thing, for example. So now it has to come to 0.5, for example, 0 to 5, 0 to 1, 1 itself will take, okay? So what I'm saying is, this is the pointer. Okay, this is the pointer on the scale. Now, when I put a weight over it, what happens is this first order system will will not directly come over here. In zeta is equivalent to 0, what happens is it will keep on vibrating. Zeta is equivalent to 1. It takes some time, t equivalent to 5 seconds. But slowly from 0, slowly it will come and reaches the steady state. Okay. But when it is time is it is zeta value is greater than 1, what happens is it takes more time equivalent to 7 seconds. There is no oscillations. Very slowly it will come and show you this one. So that is the meaning of it. This is how a second order system will behave when you give a step in. Any doubts in this? Can you? Okay, so if you are really inquisitive, you look at the equations and go to any online plotting softwares, give that function, and you can see the graphs varying like that. Okay, so I am also showing you here a 3D kind of a signal over here. You can see that the critical damper value C by Cc, are you able to see? So this is the zeta value. When your zeta value is varying, what in a 3D plan with your time versus the amplitude ratio, you can see here the amplitude. You know, right? What is amplitude? Amplitude means for a wave, the distance between the crest and the trough. Correct? This and this. This is the amplitude, right? And that the number of oscillations per second, the repetition, the number of oscillations that are repeating per second is frequency. Okay, how many times it is the same thing is repeated per second is your frequency. These things you know. So what I'm trying to do is I'm trying to take the amplitude ratio, this ratio how it is varying, the distance by the with respect to time by the input amplitude, actual input amplitude, and then you are also looking at the frequency wise with respect to t frequency shift, and you are kind of seeing over here that your non-dimensionalized time. This is omega n into t, right? So you can see over here that when you are c by cc, when it is 0, you can see this value it's oscillating. So the amplitude is bigger, amplitude ratio is bigger in the third direction. But did it get to a steady state? No. Within 20 seconds, it keeps on going. Again, if you further go, it will show the same thing. This is the nature of underdamped system. When it is within the, this is not undamped system. When it is within the underdamped system, you can see as your zeta value is increasing and reaching towards 1, the peak and the amplitude value is reducing. At the same time, it is coming to a steady state. Right? This ratio, this value amplitude is slowly reducing. Here also, amplitude is slowly reducing. And by the time it reaches 1, there is not bigger amplitude. But when it comes to the 1.5 value, you can see that amplitude value, amplitude over here, is not same as this. Okay, but slowly it will reach the steady state value it will reach. I hope I am clear with the behavior. Any questions I would like to take? Can I assume that no questions? Right. Next thing is harmonics. So we are only dealing with, we have so far dealt with the when you are giving a simple step input unit step function, how the first order system is behaving, second order system is behaving, and then the second order system, first order and zeroth order systems are behaving. Those things we have so far have looked at. Now the second and more complex kind of an input in which we generally see the steady state response, the unit step function response is relevant towards steady state. That means the weight or the input function is not varying with respect to time. But many a times we may be interested in the transients, the unsteady thing. Okay, so there we would like to see how this kind of things can be studied when a harmonic input is given to these kind of systems. Suppose there is a first order system, how it will behave. If there is a second order system, how it will behave. Those things we may be interested to have a look at. So we can have a look at it now. So before going to that, any general dynamic system, dynamic in the sense with respect to time, if it keeps on changing, we call it as a dynamic system. Any measurement system which is capable of taking dynamic measurements, so that kind of a system, we will study the behavior of those systems using, we will be using the three components. One is the frequency response. The second one is, I would like to write, what is that? I will try to find out what is. I will try to look at that by means of how the frequency is, how it is responding with respect to frequency. Second one is amplitude response. The third one is the phase shift response. The fourth one is swing response, we call it, but it's not that important. Can anyone of you understand why these responses are important? Just think and answer me. What are these responses actually? Is there anyone in the class or not? Nobody's answering. Say something. I mean, if you keep silent, then how do I understand? Hello. So whenever we are giving a dynamic input, right? For example, I'm putting a weight like 2 kg in the first second, 4 kg in the second, 6 kg in the third second. Likewise, I'm giving. With respect to time, my thing is varying. After reaching 6 seconds, I'm taking again 4 seconds. I'm taking again 2 seconds. And then again, this is repeating. Again, I'm keeping 4 seconds and then 6, and then again 4, and then again 2. So this is my input that I'm giving, correct? So when I'm giving this kind of an input, how my first order system will respond? How my second order system will respond? So here it is dependent on time. So when I give time equivalent to 1 second, okay, so the measuring system, so let us say this is measuring system recorder, for example. Measuring system recorder. Whether at the first time tau equivalent to 1 second, is it showing anything? Or at 2 seconds, it has reached to 4. At 2 seconds, it may be showing it to be 2. And when it becomes at 2 seconds, weight has become 4, and it is output is only showing this input. This is input. This is input. Don't get confused. At time t equivalent to first second, my weight is 2, and in the output, in the first second, it is not showing anything. The second second, it is showing 2 kg weight, and in the third second, it is gone to 6, but it is showing 4. So there is a kind of lag in this two things, right? There is a kind of lag in these two things. But however, even though there is a phase shift, we call it if it is a signal kind of a thing, but in general, even though there is a time lag over here, but it is able to reproduce the actual input, correct? 246 is varying, it is able to produce from 246. It is able to produce, but there is a lag in the timing. It is not exactly the same time, it is not able to show, but it is taking some time. So if you know the timing properly, if you adjust the timing properly, then obviously you will be corresponding to this, right? You are able to corresponding to the input. What input you are actually measuring, you will be able to do. Suppose if it is a sinusoidal wave, if it is in the form of a harmonic, the input is in the form of a harmonic. How this is an input? How do you know that this input is measured accurately? Okay, for that we will look at in terms of frequency response, we will look at its amplitude response, we will look at its phase shift response. This is what I'm talking. Clear? I'm just talking about this input is faithfully produced by the measurement system. We will be knowing about that, or we can certify that this measuring system is able to reproduce the input or a dynamic input after looking at by looking at these three things: frequency response, amplitude response, and phase shift response. Am I clear? This is what we will be trying to do. So in the first order system, just a moment. So now first we are giving a harmonic function. And then we are looking at the behavior of the first order systems. Okay, we are looking at the behavior of the first order systems. So let us, I am taking here a small sinusoidal kind of a thing. Okay, your input is x of t equal to a sine omega t. Okay, now what is a, what is omega? Here a is the amplitude, the distance between the crest and the top. Omega is your frequency, which we call it as the cyclic frequency. We call it as cyclic frequency means there are two things again. One is called the circular frequency and the other one is called the cyclic frequency. Okay, and cyclic frequency refers the number of cycles that are taking place per unit second. Whereas cyclic reference means you are kind of reproducing this harmonic motion with circular reference. So you generally use 2 pi ft. Okay, so the certain number of revolutions are also being taken care. So that is basically your circular frequency. Okay. Any doubts in that? I mean, should I clarify or is it okay? Okay. So the solution for the first order equation in this case, with this input, and you know that you have written no a power n into dx d power n x by dn. So if you take that expression, the final one is a1x. So if you use that a1 by a naught into that expression, and when the order is 1, that expression is equivalent to a sine omega t, and when you try to solve the generalized equation, you will be getting an output value like this: y of t equal to c e power minus t by tau, okay, plus a by a naught into 1 plus omega t square whole power 1 by 2 sine omega t minus tan inverse of omega t. This is what you will get. Okay, so now from this, what you can understand, I try to make it very simplified, where m is nothing but your 1 by 1 plus omega t square whole power 1 by 2. K is your 1 by a naught, static sensitivity, and a is the amplitude. Okay, I'm not doing anything. I'm just taking a as a, 1 by a naught as static sensitivity k, which is what we have defined earlier, and 1 by 1 plus omega tau whole square power 1 by 2. This is basically I'm writing in the form of m, and then sine omega t minus tan omega t tau, I'm taking it in the form of a phi, which is what I call it as a phase angle. Okay, phase lag or phase angle. So now I have defined it. What is m here? What is m here? M is the magnitude or amplitude ratio. Okay, so magnitude or amplitude ratio. We are calling this 1 by 1 plus omega tau whole square whole power 1 by 2. We are calling that to be a magnitude or amplitude ratio. Okay, so the solution, we are making it simplified. M is the amplitude ratio, K is the static sensitivity, and A is the amplitude, and phi is the phase angle. So you can see over here, we are also defining another term, the time lag, which is defined by phi, which is the phase angle or phase lag, by omega is the frequency. Okay, so suppose now what we can look at this particular thing, how the input of this will keep on changing when we give an input is, the thing is, the thing is, just a moment. Right. You can see over here that the amplitude ratio of the output for a given input, okay, for a given input of a sine omega t, your amplitude is reducing. Okay, your amplitude is reducing. Your amplitude is supposed to be like this: 1 to minus 1, it has to be 0 to 1, 1. So 2 it has to be. But you can see here 0.4, 0.4, 0.8 is the amplitude. So there is a reduction in the amplitude. Let's see. And again, there is a frequency are almost, it is same as the frequency, but you're also seeing some phase lag in the output. Okay, you could see that there is some phase lag in the output. So you are having some what we call time lag over here, delta t, which is measured by the particular. So when you give any sinusoidal input, you can expect that the amplitude may vary and there will be phase shift with the expressions, but the frequency may remain constant. On what factors does it depend? You can see over here, if the frequency is very high, what happens with the frequency is where omega becomes very high, what happens as the frequency becomes very high from this expression? This is the non-transient term. It's not a steady state term. Okay, over a period of time, it will vanish. But this term will remain constant. I am saying A as the constant. Suppose if M, what happens to M if omega is very high? Is there anyone in the class or not? It's a simple mathematical equation, no?
M decreases.
Yeah. When your frequency is increasing, that means in a 1 second, if the repetitions are pretty high, then obviously what will happen? Your amplitude ratio, you can see here, M value will become reduced, and when M is reducing, your amplitude is also reducing. So instead of 1, if it is 0.5, your amplitude is reduced. That means what? That is the meaning of it. Okay, so you can expect as these values are increasing, so obviously your amplitude goes on reducing. So the more the frequency, the lesser the amplitude. So for the given input with higher frequency, your amplitude goes on reducing. So your frequency has to be somewhere around the natural frequency. And this is one of the major look. And you can also expect the phase shift, how much phase shift is happening in that, and time lag, what is happening. Those things you can find out from this particular expression. So you may be given in the exam some kind of an input over here. You may be asked to find out what is the amplitude ratio, what is its phase lag, and what is its time. So these are the things that may be expected in the. So you can expect this kind, and when you even look at the expression, you can get some more conclusions. Please have a look at it. So this I am giving you as a work. So just have a look at on how these values will change. You can have a look at this. Okay. Let's move on to the responses to the changes and for a harmonic function if it is a second order system. For example, if you are giving a second order system input as a sine omega t, and the solution generally we get is mka sine omega t minus phi. So this is the magnitude ratio. So we have written mka, right? So this m, static sensitivity into amplitude. So this m is very, very complex over here. So that is simplified like this: 1 by 1 minus omega by omega n whole square plus 2 zeta omega by omega n whole square. So here we have zeta value, and generally the phase angle is given by zeta omega by omega n, and likewise. Okay, so it's very complex in nature. So using these equations, what they have tried is they try to write down a relation between the amplitude ratio, which is x naught by f naught by k, frequency ratio, which is omega 1 by natural frequency by its actual frequency or dynamic frequency. And similarly, they have also drawn another graph which shows the phase angle variation with respect to frequency ratio. Okay, so now you can see that it depends on two things. One is zeta value, it depends on the other one is frequency ratio. Okay, so now you can clearly see what happens to its amplitude when the damping coefficient is varying. For example, you can clearly see here for values up to 0.3, okay, clearly up to 0.3, what zeta value from 0 to 0.3 or kind of 0.4 also, okay, up to 0.4, what you can observe is your amplitude is remaining the same. Is it varying? Are you able to understand what I am talking about? what I'm saying is, sorry. What I'm talking about is, okay, this was already recorded, that is the problem. 1 second. Just here I can see. Just another 5 minutes, man. You have another class after 1:30? 2:30, you have another class?
No, sir, we have on 4:33.
3 only. Can I take 5 minutes just to explain?
Okay.
I'm not getting the cursor. That was what I'm. So can you look at most important thing is cursor. Yeah, this is fine. I think now the cursor is you are able to see, right? My cursor.
Yes, sir.
Yes, sir.
Yes, sir.
Yeah.
Yes, sir.
Yeah. Now you see here the zeta value when it is 0, right? What I want to show you in this exactly is, you have given a curve like this, for example. Your this is the input you are giving, for example. Okay, this is the input you are giving, and what you generally want is, you want to also find out whether the measuring system is able to produce the same thing or not. That is the question, right? So if you have a measurement system, now you will understand from the system properties, measurement system properties, how it can behave. That is what these graphs are telling you. If I have an input like this with certain so and so amplitude and so frequency, and the system properties are like this is a second order system and its properties are like this, then what can you expect out of that system for a given input as shown in the figure? Whether there will be any distortion in the amplitude, whether there will be any reduction in the amplitude, or whether there will be any phase shift in the amplitude. How? So these factors will define your measurement system. Are you able to understand what I am trying to convey? You are designing a measurement system in such a way that whatever the springs and masses and all you are keeping in that, they should work in certain area to faithfully reproduce the input. Correct? Suppose if my factors are varying way behind, then I will be knowing from these graphs that it will not provide a faithful reproduction of the input. So this helps as a designing kind of a thing. You understand? So it will tell you as governing or performance characteristics kind of thing. Okay, these two graphs are a second order system. You can see over here, this is the input that we have got, and our zeta value is 0, 0.3, almost up to 0.4. You can see that. Is your amplitude varying? Amplitude ratio means input amplitude to the output amplitude. Is it remaining 1 or is it varying? Hello?
Remaining one, sir.
Up to remaining 1, up to what? Probably up to where it is actually remaining 1. If it is 0.3, it is remaining to the frequency ratio of 0.3, correct? See, 0.1 logarithmic it is, and of 0.1, 0.2, 0.3. So up to 0.3, you are able to see that the amplitude remains the same. So whatever amplitude I am getting from the output is same as the input. Up to what? My frequencies are a frequency ratio. What is this frequency? Frequency with respect to its natural frequency. This ratio is up to 0.3. If it is within this range, and my damping coefficient is underdamped up to 0.3, then I am pretty sure that my amplitude will not vary. Now, what happens if my amplitude goes on increasing, or if my frequency ratio goes on increasing? You could see that if you are going on increasing your amplitude ratio for 0.3, 0.4 up to 0.707, it is going on increasing. Okay. So now what you can observe from this? Now you can have this kind of an output you may expect. Okay, so the amplitude is varying, the amplitude is high. The ratio is 1.5 times, 2 times. So it's going on higher. Up to what? Up to 0.707. And after 0.707 and after we cross 0.7, what is happening? Your amplitude ratio slowly it's a gradually reducing graph. That means it goes on reducing. So depending on what frequency levels you are working on, you should be you should be clearly knowing. Okay, and based on that, you can what is the viscous dampening factor that you are using. If you know that, then you can expect that whether your amplitude goes down or your amplitude increases or your amplitude remains constant. So these are the things that we can understand from this particular graph. Am I clear with this?
Yes, sir.
So for large values of zeta ratio, the amplitude is reduced substantially. For lower values, for very low values of CC and with very high frequency, that means if you are giving the frequency is pretty higher, the output may be so annoying. That means it may be going distorted. You may not even understand what is the output also. So from this, you will be able to understand. For a simple example, if you have a spring, I will show you the spring kind of a thing. If you slowly move this upwards, okay? If you slowly move this upward, what happens? The spring and this will work, and the displacement will come to x2 here. This will move slowly. Okay, let us say that x2 is the output, x1 is the input. What happens if you simply move this very slow frequency? It will oscillate very slowly. But if you move this with violently, that means if the frequency is more, this will move very violently, that the frequency, the amplitude will be very higher depending on what C value you are providing, based on what damping coefficient you are providing, what spring value you are providing. So sometimes it will not produce the same input, but some junk thing it will be producing. So you should be able to figure it out in what ranges or constraints I'm actually working in. Clear? That is what the frequency and amplitude ratio, this thing will tell us. Similarly, you can also see that the phase shift. Phase shift means, as I told you, the time factor. So for example, if this is the curve with different times, now I may be able to get another curve. My output may be starting over here. Same curve, but it has a phase shift of some 30 degrees, for example. So that also can be formed. It is a very strong function. Phi is a strong function of zeta, frequency ratio. Both it is depending, this phase angle is dependent on zeta and frequency ratio. Here also you can see the amplitude ratio is a strong function of zeta and frequency ratio. So therefore, you can see from here, this is 0.3, this one is 0.3, 0.5, and then you are slowly increasing this value. So you can see that the phase shift characteristics are almost, you can see these two curves, they're almost linear up to a value of 0.5 frequency ratio. up to a value of 0.5 frequency ratio. They're almost linear, right? They're only varying. If you see the phase shift here, it's 30 degrees, it's 30 degrees. So for low damping ratios up to 0.5, you could see that it kind of, within the frequency ratio of 0.5, it is basically almost, there is not significant phase shift. It's almost 30 degrees phase shift, you could see. But your values are going on increasing, then what happens? Your phase shift will become very, very critical. How much it is phase is changing, we should be aware of. Okay, so you have a critical value of 0.707 here, which you can see there, that it is actually varying in continuous change with the frequency ratio. Okay, so that is kind of a critical kind of a thing that we can take in designing these second order systems at this dynamic measurement. I hope you are able to understand the behavior of these systems. That is what is expected. I'm not expecting you to remember all the formulas and all. What I'm expecting out of this particular class is, if you are giving an input, how the first order or the second order system, they will try to behave. And specifically, if you go for electrical measurement systems, like which are dependent on voltage and using voltage inputs and all, you should be really knowing these things. Okay, how the natural frequency work, how the damping coefficient will affect the amplitude ratio, how the phase shift is getting affected. These things you should have a basic idea. With this, I'm stopping my class. Any doubts I would like to take, and I'm given a simple problems over here. Please go through these simple problems. Once again, I will send this to your mail ID. Please go through these simple problems, and then next class we will decide. Tomorrow's class we will discuss these problems, and then we will move on to the next topic. Up to this, we are only studying about, so far whatever we have studied is basic terminology, basic measurement system components, and for what are the types of inputs and how the measurement systems are classified, and for each input, based on the input, how each measurement system is behaving when it comes to its output and producing their outputs. So these are the things that we have studied. So these are the very fundamental aspects we have studied so far. And in the next class, we will see the experiment part. So what are the types of errors, how errors will come in, and when errors come in, how do we estimate the errors? How can we say a measurement system uncertainty? These are very, very interesting and very important topics for mechanical engineers, especially for those who go for quality control and all. These are most important things, right? So those who doesn't have any doubts and all, they can leave, and those who have doubts, I'm very happy to. Will you share these slides? I'm sharing it, right? You are not able to get?
First class slide is not shared with us.
First class, huh? Okay. First class is only introduction, so I will do that. This one I will send immediately. Now itself I will share. Those are smaller things. Is that will you share recorded lectures? Yeah, I'll do that also. Okay, so thank you. Okay, thank you, Sahil. But is that are you people able to understand what I'm trying to say, or is it redundant? I'm taking long time to explain or something.
No, sir, we are able to understand.
Yeah, but the explanation is enough, or it's redundant? That's what I'm. Because there will be some students who may not be able to understand it at once. That's why.
No, sir, it's fine.
Okay. Fine. So those who are having interest, just go to the Beckwith and this textbook, not for the sake of marks and all, especially when you work with electrical instruments, you need to have this knowledge. So those who are interested in the measurements, or if you want to become a good experimentalist and all, there is a good amount of explanation given, which I just confine it to to single lecture. You can go through that and just keep on reading like that. It's beautifully explained in Beckwith. In Beckwith, what they have done is, in terms of Fourier transforms, in terms of how the curves will behave, everything they have given nicely. And in Holman, same thought, almost more or less the same things I explained. So Beckwith, if someone is interested, go and read that book. That will be very interesting. Okay, for this topic, some extra information you will be able to get. How the inputs are varying when we change the frequency, when we change the amplitude. We can, there's this schematic representations of that are given. You can have a look at that. Okay. So if you have no doubts, then I will stop this class. I hope tomorrow's class you just look at the Tuesday in your calendar, you will have that class. I think I put it as a repetitive. So definitely you will get the link and just simply join in that class. Okay.
Okay.
All right. Any questions related to the lab? Others, they can leave. If you are getting bored, you can leave. Others who